It's too mild of a flavor.
Lesson 8.3. We are continuing to talk about graphs. It's not that we are really graphing things today, but we are talking about some of the aspects of graphs. So in those, and I'm going to refer to the graphs we did yesterday, but in those graphs we talked about yesterday, they had asymptotes. Well, one of the big things we're talking about today are asymptotes. So we're going to look at several different aspects of graph and how you can look at an equation and find those pieces of information. Okay, so all about trying to understand the graphs. Now, I'm going to spend a good portion of time here just talking about this information on the chart, adding some information to this chart, and then we'll go to the back and do an example or two. Now, I will say what you are provided or given on your quiz and then eventually a test is I haven't handed them out because I haven't made the copies yet, but I will provide the direct and inverse variation forms. So you'll have those equations. So as long as you know how to use them, it won't be a big deal because you'll have them provided. It won't be a matter of which is which. You just have to know how to use them. And then this chart that is right here, I'll provide that. So again, it's understanding what all of this means and then just knowing how to use it. Okay? So first thing we're going to talk about is a vertical asymptote. We talked about vertical asymptotes yesterday, right? Vertical asymptotes are always x equals a number. Because it's a vertical asymptote, it crosses the x-axis at some point, and so it is x equals a number. How do we find the vertical asymptote? Well, right there is the information. You find the vertical asymptote by setting the denominator equal to 0. So if I use this problem up here as an example, what is the denominator of this example here? It is 3x minus 1. So if I take that denominator and I set it equal to 0, how do I solve for x if it's 3x minus 1 equals 0? We're going to add 1. We're all just doing it. That's why you're not telling me, right? We add 1 to the other side. It's 3x equals 1. And then to get x by itself, we're going to divide by 3. That's an example of how you find a vertical asymptote. Okay? It's an example of how you find a vertical asymptote. And we'll, as I said, we'll use that example and you'll be using that in homework. Now, before I move on to the next part, vertical asymptotes. I guess let me ask this. Do you understand what it means when we talk about a graph being continuous? If a graph is continuous, it just continues, right? I like to think when I talk about a graph being continuous, I can put my pencil down on the paper and I can draw the whole thing without ever picking my pencil up. That's a continuous graph. There's no breaks in it, no stops in it, no gaps in it. That's a continuous graph. Now, when there's a vertical asymptote, our graphs yesterday had vertical asymptotes, didn't they? Remember what we were graphing yesterday? We had the two opposing curves. Can I put my pencil down and draw both of those pieces of the graph without picking it up? No, not officially. I mean, you know, you can get sarcastic and say, yeah, and just connects them, but no, we can't. So that vertical asymptote is what we call a discontinuity. In other words, it makes the graph discontinuous. So one of the things you're asked about in the homework is points of discontinuity. Anytime there is a vertical asymptote, that is considered a point of discontinuity. Okay, so vertical asymptotes are one option for a point of discontinuity. when we talk about points of discontinuity, they can be, there's two classifications, removable or non-removable. And vertical asymptotes are called non-removable. Okay. When I think non-removable, and also will make sense more when I get down and talk about holes, but when I think non-removable, it's not fixable, it's not, I can't just plug the hole and fix it, it's non-removable. Okay? So vertical asymptotes are points of discontinuity known as non-removable. So that's some information about vertical asymptotes. We're also going to talk about horizontal asymptotes. We talked about horizontal asymptotes yesterday as well, right? Horizontal asymptotes are always y equals a number. Remember, it's not just a number, it has to be the equation y equals a number. And when we talk about these horizontal asymptotes, notice it says, found by analyzing the biggest powers on top and bottom. So when we talk about the biggest powers on top and bottom, I'm talking about the biggest exponents. So you're going to look at, okay, what's the highest exponent in the numerator? What's the highest exponent in the denominator? And you're going to compare those exponents. And there's three different options. If you find the biggest exponent to be on bottom, then that asymptote is automatically y equals 0. If you find the biggest asymptote to be on bottom. Okay? If the exponents match. So notice what it says. If the biggest powers on top and bottom match. So if they match, then we're going to do the ratio of the coefficients. Now, wish I remembered my example I used this morning, but I don't. So let me create an example real quick. (3x squared plus 2x minus 4 over 5x squared minus 1. Random made-up example, okay? Don't try and figure out where it came from because the depths of my brain. Okay. What is the highest power on top? Highest power on top is 2. What's the highest power on bottom?
2.
2. So this is an example where the biggest powers on top and bottom match. Since those powers match, we're going to use the ratio of the coefficients. What are the coefficients of those terms? So coefficients being the numbers out front. So what are the coefficients of those two terms? 3/5. Okay. 3 over, did you say 3 over 5?
No, I said 3 and 5.
3 and 5. Well, they are 3 and 5. The coefficients are 3 and 5. That's a valid answer. And so this example, my asymptote would be y equals 3/5. So that's an example when the highest exponents match. You take the numbers from the front of those terms and make them into the asymptote. And then there's a third option. So we looked at when the biggest power is on bottom. We looked at when the powers match. So then the third option has to be when the largest exponent is on top. And in that case, there are no horizontal asymptotes. And again, we'll get to apply this some on the back. I'm just trying to give you some options here so you can see it. And actually, let's look at this example here. If we look at this example that we were given up at the top of the problem, what's the highest power on top? It's that 3x to the third term, right? So 3. What's the highest power on bottom? The 3x to the first. Where's the biggest power? On top. So what category does this fit into? Because the biggest power is on top, this is an example of there being no horizontal asymptotes. Okay. Okay, so that's some information about horizontal asymptotes. The last piece we're going to talk about, well, it's written here, I have some information to add, are holes. Okay? Graphs sometimes have vertical asymptotes, they sometimes have holes. Now, I don't know, what comes to your mind when you think about a hole? I'm not thinking about what I'm drawing here. There's a graph that's an example of a hole. Because it looks pretty much like a solid graph, except there's a little gap in it. Okay? It's not where the graph is going two totally different directions like an asymptote. There's a gap in it. If I were to graph something on my graphing calculator with a hole, it would just kind of look like this. Now, typically when we draw a graph with a hole, we usually kind of put the little hole there to represent it. But this is an example of a hole. Can I draw a graph with a hole without picking up my pencil? No, I technically have to pick up my pencil. So guess what? A vertical asymptote was a point of discontinuity. Guess what? A hole is also an example of a point of discontinuity. Sorry, I have to focus to spell discontinuity. Okay, holes are an example of a point of discontinuity also, except they are what we call removable. So points of discontinuity can either be non-removable, and that's a vertical asymptote, or they can be removable. So work to remember those however you want. My weird thought is, okay, a hole, I could remove a piece in a hole or put a piece back in a hole. So it's removable or it's fixable. A vertical asymptote, I can't just remove a piece there. It's a whole big gap. I don't know if that makes sense or not, but wrong button. As we talk about holes, holes always are x equal a number, so a hole occurs at some x value. And they occur if the functions on top and bottom can factor and reduce. The hole is the answer to the canceled piece. So when we go to these examples on the back, we're going to bring back our factoring skills from first semester. In fact, this chapter brings back a lot of factoring skills. So that will be second half of the chapter. But the idea will be, if you can factor something, like we're going to be talking factoring into parentheses type thing, and there's a factor on top and a factor on bottom that are the same and can cancel out, those are going to represent holes. I will show you an example of that on the back. Okay? That's the easiest way to show that one. Now, before I flip to the back of the notes, got 3 other topics I need to include here that weren't originally included in the notes, but they do come up now in the lesson, and so I want to make sure and mention them. One of the other pieces you'll see mentioned in homework is they will be asking you about the domain again today. Okay? What kind of domain did we have on those graphs yesterday? Okay, it was all reals except x equals a number, and that x equals a number was the vertical asymptote also, wasn't it? Well, the domain's going to be the same on these. It's still going to be all reals except any vertical asymptotes or holes. So these two pieces that say x equals, Okay, so to kind of give you a hint of what you're going to be looking at, your domain will be, again, all reals except this time it's going to be vertical asymptotes or holes. Okay, so I suggest you write that information down so you have it for later, right? We're also going to talk about x-intercepts. X-intercepts, so where a graph crosses the x-axis. And traditionally we say, okay, in order to find an x-intercept, you put 0 in for y. Which, in equations like this, putting 0 in for y basically means we need the fraction equal to 0, which means we need the numerator equal to 0. So in order to find x-intercepts, we're going to set the numerator equal to 0. Yes?
How can we have an x-intercept if the line is supposed to just be getting closer to it and not touching it?
Oh, like when we have horizontal asymptotes? Is that what you're talking about? It's like the horizontal asymptote is like what the graph is when it runs against and it's getting closer and closer and closer and never touching it. The trick with horizontal asymptotes is that that behavior is as the graph is going like out to infinity, like way out to the edges. In the center of the graph, we can cross through a possible asymptote. It can happen in the center of the graph. So it could cross through the axis then. And I'll show you an example. Actually, I'll graph one of our examples from the backside.
That might be better.
But it can, vertical asymptotes, a graph will never ever cross or touch it. Period, end of statement. Horizontal asymptotes will never cross or touch it as we go out to the ends, but it can in the middle. That's a little bit different. I talk about that concept more in pre-cal than I do algebra 2, but it's a little bit different. Okay, one other item before we turn the page, and that is y-intercepts. With y-intercepts, easiest thing to do is let x equal 0. And so we're going to do just that. Let x equal 0. So we'll take 0, we'll put it in for x, and we'll do the simplifying. Okay, so we have a lot on that front side. You got it all? Because you're going to want it all for homework, I promise. That's part of the reason I've added so much. Now, on the back side, we'll see what we can get through. I want to talk through at least 2 examples here. We'll see how things go. On the back side, we're going to, all those topics we just talked about, we're going to practice them all. Okay? Officially, the directions say to identify all horizontal asymptotes, vertical asymptotes, and holes for each function. But we're also going to talk about domain and x and y intercepts. Again, trying to prepare you for different things you're going to see in homework. Now, notice they give us a hint here. Go in this order. They suggest that we start by finding holes, then you find vertical asymptotes, and then you find horizontal asymptotes. I'll be honest, I don't care when you find horizontal asymptotes. They can be first, they can be last. But it does matter that we need to find holes first and then vertical asymptotes. Because if something is a hole, it can't be a vertical asymptote also. Okay, so we need to find holes first, and then we'll look at vertical asymptotes. So, looking at example 1, y equals x plus 3 over x squared minus 4x plus 3. First thing we're going to try and find are any holes? Okay. Now, we're going to do lots of flipping back to the front side, right? What did it say about holes? We have to factor, right? Holes occur if top and bottom can factor and reduce. So one of the first things you're going to do with every problem is you want to factor it. Okay, dig deep, guys, dig deep. You can factor. I know you can. X plus 3. Well, if something like x plus 3 factors, the only thing we can do is like a GCF. X plus 3 have anything in common? No. X plus 3 is just going to stay x plus 3. Denominator. Okay, guys, dig deep. It's in those brains somewhere. We need to factor x squared minus 4x plus 3.
Just the parentheses.
Remember 2 parentheses? You know this. As I said, dig deep. It's in there. X squared breaks into x and x. Disagree.
Wait.
We need 2 numbers that multiply to be 3 and add to be negative 4. What numbers multiply to be 3? I mean, 1 and 3 are your main options for multiplying to be 3, yes? They're not factors, they're not whole numbers. Okay, so 1 and 3 are where we're going to go. We're not going to be difficult. If they multiply to be a positive, both numbers are either positive or both numbers are negative. If it adds to be negative 4, we're going to make them both negative.
I don't know why, but I could not think of a way to do the 3 and the 4.
I thought mine was
Well, again, I'm hoping you dig deep enough, it'll come back to you. I'm not going to just leave you high and dry and not explain it, but it's got to come back to us. Now, are there any identical factors, top and bottom, that can cancel? On top, my factor is n.
I needed him to caddy for me on the front nine, so that's why we were.
That's why it took so long. Okay.
All right, thanks a lot.
You're welcome. Okay. X plus 3 is what my factor is on top. Are there any identical x plus 3s on bottom? No. I have an x minus 1 on bottom. Is there an x minus 1 on top? I have an x minus 3 on bottom. Is there an x minus 3 on top? Are there any identical factors? No. So there's no factors that can cancel. So are there any holes? No. I know, all of that work and there's no holes, but we have to check it. So no holes, and I'm going to write here as a side note, there's no holes because no factors cancel. And you can just write none, but are you going to understand when you go back and look at this as an example later? Some may not. Okay. And let me backtrack for a brief moment. Realize, because I know it's probably out there and just no one expressed it. When I first started this problem before I ever factored, no, you cannot just cancel the 3's and cancel an x. We cannot cancel, you can only cancel factors, so pieces that are multiplied. You can't cancel pieces that are being added to other pieces. You sometimes hear in math that those pieces that are being added to other pieces are married to those other pieces, and we can't cancel them out. Okay? So just kind of be aware of that. They have to be factors to cancel. So, good reminder there. Okay, there's no holes. After we check for holes, we're going to check for vertical asymptotes. I'm going to say flip to the front side of your notes again, right? What's the rule for vertical asymptotes? Okay, found by saying the denominator equal to 0. It's right there in writing. This is why I wrote it all out for you. So, Now, when we say denominator equal to 0, you could go the original denominator, but that's no fun. You already factored this, yes? This is part of the reason we already factored. Set each factor equal to 0 is the easiest thing. So I'm going to set x minus 1 equal to 0 and x minus 3 equal to 0. If it's x minus 1, we're going to add 1 to both sides, and we're going to get x equals 1. If it's x minus 3, I'm going to add 3 to both sides, and I'm going to get x equals 3. So we end up actually with 2 vertical asymptotes, x equals 1 and x equals 3. Now, let me ask a question. Now that we have our holes and our vertical asymptotes done, are there any points of discontinuity on this graph? Where can points of discontinuity happen? At holes and vertical asymptotes. Did we have any holes or vertical asymptotes? Yes. So we have points of discontinuity where? At 1 and 3. So I'm going to put information here that we have points of discontinuity, and that's at x equals 1 and x equals 3. Are these points of discontinuity removable or non-removable? And how do you know they're non-removable? Because they are vertical asymptotes as opposed to holes, right? Anytime it's vertical asymptotes, they are non-removable. And yes, because I told you, but. Okay, moving along, moving along. We've done holes, we've done vertical asymptotes. Now we've got to do horizontal asymptotes. Are you flipping back to the front side? What's my horizontal asymptote rules? Found by looking at the biggest powers on top and bottom. So highest exponent on top, highest exponent on bottom. Okay, well, I would go back to the original problem before you factored. What is the highest exponent on top? This x to the first term, yes? What is the highest exponent on bottom? Highest power on bottom is the x to the second. What do you need to notice here? Biggest power is on bottom. So if the biggest power is on bottom, what's the asymptote? Y equals 0. And your reasoning is because the biggest power was on bottom. Okay, I told you I added those 3 other items, right? We're not going to be doing B, so I'm scribbling out B and I'm using that area. Because I still need to talk about domain and our intercepts. Domain. Even think back to yesterday for this one. What about my domain?
Oh, but
All reals but something.
X equals 1.
Okay. It's all reals except any vertical asymptotes or holes. We don't have any holes, but we have vertical asymptotes. So, all reals except x equals 1 and x equals 3. And actually, I'm just going to put a comma between them. So all reals except x equals 1, x equals 3, and that's because those were my vertical asymptotes. X-intercepts. What did it say for x-intercepts? Numerator equal to 0? What's my numerator?
X plus 3.
X plus 3. Okay, so numerator equal to 0. So x plus 3 equals 0. If it's x plus 3 equals 0, how do I solve it? Subtract 3, and we're going to have an x-intercept at x equals negative 3. I'm fine with x equals negative 3. What if Math Excel expects an ordered pair? Yeah. X-intercept as an ordered pair. The x value is negative 3. The other half of an intercept is always 0. I don't remember for sure what Math Excel wants, but FYI, right? And one more. Y-intercepts. What was the rule for y-intercepts? Okay, we're going to let x equal 0, which means I'm going to put 0 in for x. You can either use the original equation, put 0 in for x here, or you can use the factored equation. Whatever makes you happy. So if I do this, it's y equals 0 plus 3 over 0 squared minus 4 times 0 plus 3. Well, on top, 0 plus 3 is 3. In my denominator, 0 squared is 0. 4 times 0 is 0. Plus 3, so that is 3. And what is 3 over 3? 1. So my y-intercept is going to be y equals 1. If Math Excel forces you to do an ordered pair, you're going to say 0, 1, because it's a y value of 1, and we put 0 in for x. Okay. I know, that was a lot, wasn't it?
Yes.
There's a lot of pieces. You're not going to necessarily have all the pieces on one problem. But if I'm recalling correctly, you see all the different pieces throughout homework. So that's what I'm trying to make sure you're set for. Now, we're going to go down. I'm going to go to my next page. We're going to talk about C. We won't necessarily get all the way through C, but I'll be happy if we can talk about holes and asymptotes, because those are the biggies that are newer. Okay? We're doing C.
But no, like, is it okay if we go over into the one we're writing?
I'm not even going to get all the way through C, so. Yeah. B, C, D, we can't tell what we're all saying. Okay, first question is holes. When we talk holes, we have to start by factoring. X squared minus 3x minus 4. Well, guess what? It's going to factor. X squared breaks into x and x. What are my options for multiplying to be 4? 2 and 2, 4 and 1. Which one's probably going to work if we need 3 in the middle? It's going to have to be a combo of 4 and 1. If it multiplies to be negative 4, it's a positive times a negative. If it adds to be negative 3, yeah, larger number negative, so negative 4 plus 1. What happens to be in the denominator? X minus 4. Hey, guess what's happening here? Do we have a factor that is the same? Yeah. We have a factor of x minus 4 that can cancel with x minus 4. And so because that x minus 4 can cancel, that's going to represent a whole. And so I'm going to say because x minus 4 cancels, your whole is going to be at x minus 4 equals 0. If you have x minus 4 equals 0, what does that become? Add 4 over, there's going to be a whole at x equals 4. That's an at symbol, by the way. I tend to put an at symbol. I don't know, my brain, I just hear there's a whole at x equals 4. So, not that you necessarily have to have the at symbol there, but.
So, what do you get x plus 4?
That's going to hang around. We'll use it later.
Okay.
Okay. It doesn't affect wholes, though. It's still part of the problem. Now, I'm going to stop here, or pause here real quick and ask, what's this tell me about points of discontinuity? There's a point of discontinuity at x equals 4, and it is removable because it's a whole. Sound familiar? So just going to throw that in there before I forget. There's a point of discontinuity at x equals 4, and because it's a whole, we know it is removable. Okay. What do you have to find after wholes? You have to find vertical asymptotes. Now, as we work to find vertical asymptotes, how do we find vertical asymptotes? You set the denominator equal to 0. But what happened to our denominator in the last part of the problem? It got canceled. So here's the deal, guys. You cannot have a whole and an asymptote at the same place. It's one or the other. Since there's a whole at x equals 4 and there's no other denominators, guess what? No vertical asymptotes. And again, my reasoning, there is a whole at x equals 4, and we can have whole or vertical asymptote, not both. Okay? Whole or vertical asymptote, not both. Real quick, we've got to talk about horizontal asymptotes real quick because I feel like that's something we're going to be foggy on. Horizontal asymptotes. What do we look at? Powers. Biggest power on top was x squared. Biggest power on bottom, x to the first. So that means there are no horizontal asymptotes, and that's because the bigger power is on top this time. Okay. No, we did not get to domain x and y intercepts, but I think those are a little bit easier and better with those. Yes, I want you to do the homework. Okay? I think you have all the information.
2 days.
You just have to apply it. So do the lesson A3 homework. Come back with any questions on Monday. And have a good weekend.